Hello dear friends, welcome to a lecture on ring theory. In this lecture, we shall study two results regarding polynomial ring. Earlier we have defined polynomial ring and we have proved a result that a polynomial ring f of x over a field f is a commutative ring with unit element. In this lecture, we shall prove that the same polynomial ring f of x is an integral domain and also the polynomial ring is a Euclidean ring. So, these results we shall prove one by one. So, first I have written the result as a lemma that f of x is an integral domain. Polynomial ring is an integral domain, that we shall prove. And polynomial ring we know is taken over the field f. That means coefficients of the polynomial belong to the field f. So, we shall prove this result. Let f of x be a polynomial ring where f is a field. That means it is set of polynomials of the form a0 plus a1x etc. And that is we have f of x is equal to the polynomial set of polynomials or symbols of the form a0 plus a1x plus etc. am x raised to m and such that m is non-negative integer and ai belongs to f. So, this is the polynomial ring and we have earlier proved that this is a ring which is commutative and also having unit element. Then f of x is a commutative ring with unit element. This result we have proved in our earlier lecture where we have defined polynomial ring and we have proved all the axioms of ring and plus in addition it is commutative, multiplication is commutative and it has unit element. Unit element is simple, that is the polynomial, constant polynomial 1 is the unit element. Now, what we require to prove is f of x is integral domain, and by definition of integral domain is a commutative ring with unit element without zero divisors, and therefore we need to prove that it is without zero divisor. So, therefore, we shall prove f of x is without zero divisor. Is without zero divisors, then it becomes integral domain. And what is meaning of a ring with without zero divisor? Earlier we have defined it in integral domain. That means a integral domain, R is integral domain, a b belongs to R, a into b equal to 0 implies either a is equal to 0 or b is equal to 0, then it is without zero divisor. Instead of a, b, here we have the elements as polynomials, and therefore we have to prove that in place of a and b we shall consider f of x, and see this condition can be equivalently written as or a b equal to 0 implies a is equal to 0 or b is equal to 0. The contrapositive of this statement, whenever a is not equal to 0 and b is not equal to 0. B is not equal to 0 implies the product AB also not equal to 0. Now, we shall prove this way. That means first element is not 0, second is also not 0, then their product is also not 0. And that means we shall take two elements fx and gx in this field, in this ring, and then prove that their product is not equal to 0. So, let let f of x not equal to 0 and g of x not equal to 0 in f. These are in f. Further, because these are non-zero polynomials, we shall assume the degree of fx as m and degree of g of x as n. Let f of x is equal to, and the polynomial we will express like this, a naught plus a1x plus so on up to am x power m. Here am is not equal to 0, then only the degree of this polynomial will be m, and g of x is equal to b naught plus b1x plus so on up to bn x raised to n, and here bn is not equal to 0. So we shall prove that if whenever fx is not 0, g of x is not 0, according to this property of, in place of element a b, here the elements are fx and gx. So we need to prove this fx is not equal to 0 and g of x is not equal to 0 implies their product fx into gx is not equal to 0. So this we shall have to prove. Let these are in fx, and I shall mention here only, we shall prove, we shall show that their product fx into gx is not equal to 0. So this we shall show. Then we will get the result that f of x is without 0 divisor and it becomes integral domain. Now how the product is not 0, that we shall see. Here am and bn are elements of field. We have am not equal to 0, an not equal to 0 are in f, and f is a field. Every field is an integral domain, and therefore f is without 0 divisor in f, which is an integral domain. F is integral domain because f is a field, and therefore this implies, therefore am into an is not equal to 0. It is without 0 divisor, and thus the coefficient am into an, product of these two coefficient, is not equal to 0. Now what this shows, that if you consider the product of fx into gx, and the term of maximum power term will be am into bn, or the power of term x raised to m into x raised to n in the product will be x to the power m plus n in the product. This term becomes x to the power m plus n, and the coefficient is am into bn. Therefore the coefficient of x power m plus n in the product fx into gx is which is an into am is non-zero. The coefficient of x power m plus n, if you multiply these two, the product we have defined earlier, the product will be a naught, b naught, etc., and see the maximum power term of in the product will be this term, product of these two terms, which is am bn into x power m plus n, and its coefficient is am into an, and that is not 0. This means the product fx into gx is not equal to 0. This shows that fx into gx is not equal to 0, and this is what we wanted to prove. Whenever f is not 0, g is not 0, their product is not 0, means this ring is without 0 divisor. F of x is without 0 divisor. And hence it is integral domain because it is already commutative ring with unity element. It is an integral domain. So thus we have proved our first result. Now before taking the second result as Euclidean ring, f of x is Euclidean ring, we shall write a result regarding degree of f of x, or actually we shall define what is, we are using degree of f of x, and but what is the degree of f of x, that is defined like this. Let f of x belongs to this polynomial ring where f of x, and let f of x is equal to a polynomial having these terms, and last term we can write as am x power m, where am is not equal to 0 and m is non-negative integer. Then degree of fx, or then the degree of f of x denoted by is, we denote it by, in short, deg f of x denoted by degree f of x is m, where m is a non-negative integer. That means it is the highest power term of x with a non-zero coefficient. Am is not equal to 0, and that is this is the degree of this polynomial. And regarding to degree, there are two results we shall note, as we have seen here itself. Let f of x not equal to 0, g of x not equal to 0 be in f of x, that is polynomials. These are two polynomials. Then we have, see, the degree of product of f of x into g of x. This is equal to degree of f of x plus degree of g of x. Now this can be verified from this expression, and using the definition of product. See, in this product, the maximum term or maximum power term or highest power term of x will be obtained by multiplying these two elements, and the product of these two elements is am into an x power m plus n. And because these is not 0, and these are the polynomials of a degree m and n we are considering here, and the coefficients are not equal to 0, so therefore this product is not 0, that we have considered here also, and therefore the degree of this fx into gx product is m plus n, and m plus n means m is degree of this polynomial, like this. M is degree of this polynomial, n is degree of this polynomial, and that will be m plus n, degree of fx plus degree of gx. That is first result. and second is from the same it follows degree of f of x is less than or equal to degree of f of x into g of x. This is obvious, because what is degree of f of x into g of x? That is degree f x plus degree g x, and that is greater than or equal to this degree of f x, or degree of f of x is less than or equal to this sum, because degree is a non-negative integer, and if f x is added to this non-negative integer, it becomes greater than or equal to this, means degree of f x is less than or equal to degree f x plus into degree into g x. So, these are the two results, and now we shall prove the second result as f of x is a Euclidean ring. That is our second result. And we state this as a theorem. That is f of x is a Euclidean ring. It is a polynomial ring, and we shall prove it is also a Euclidean ring. Now, what is the definition of Euclidean ring that we have studied earlier? It is integral domain. Just we have proved it is integral domain, and it is integral domain in which every non-zero element, for which every non-zero element we have to assign a d function or Euclidean function, which is a non-negative integer and satisfying two properties. That is the definition of Euclidean ring. R is Euclidean ring for every a not equal to 0 belongs to R. We assign a Euclidean function d of a, which is non-negative, means greater than or equal to 0 integer, such that there are two properties of Euclidean ring. The first is for a b not equal to 0, a not equal to 0, b not equal to 0, we have d of a is less than or equal to d of ab. That such a d function must be defined. And second is for a belongs to R, a belongs to R, 0 not equal to b belongs to R, there exist two another elements that we denote as q and R belongs to R, such that this a is equal to qb plus R, where R is equal to 0, or degree of R or d value of R, or d value of R is less than d value of p. So, this is the definition of Euclidean ring. Now, we shall have to show that this f of x is a Euclidean ring, and for that purpose what we will have corresponding changes is, instead of a b elements we have to take two elements in f of x, and the elements in f of x are polynomials, and we shall take the two polynomials as f of x and g of x, and we shall verify these two properties. So, we prove the theorem. Let f of x be a polynomial ring over a field f, and we take d function for this polynomial ring as degree of f of x. Let f of x belongs to this, be non-zero, and f of x not equal to 0. we take the Euclidean function, or which is known as d value, or d value of f of x as degree of f of x, which is a non-negative integer. Here we have defined degree of f of x is non-negative integer, and that serves as d function for the Euclidean ring required. So that is, we have d of f of x is equal to degree of f of x, that we have, and where the f of x is not equal to 0 in this Euclidean ring. So this is our d function. Now this d function satisfies these two conditions that we shall show. This is the definition of Euclidean ring, and according to this we require to prove the conditions are satisfied by this polynomials in polynomial ring. And for that purpose, so I shall write here. First, then we have in first we shall write like this. First condition, degree of f of x is greater than or equal to 0. Degree f of x is non-negative integer, means it is greater than or equal to 0, is a non-negative integer. For 0 not equal to f of x belongs to f of x, and that satisfies the condition for d value is non-negative. Second, when or for these two non-zero polynomials, for fx not equal to 0, g of x not equal to 0 in f of x, degree of f of x is, or this is just written as d of f of x by notation, is less than or equal to, we have written as a note here, degree of f of x is less than or equal to degree of fx into gx, and that proves this condition. D of a is less than or equal to d of ab, degree of f of x less than or equal to degree of fx into gx. And second condition is for fx and second g of x not equal to 0 in f of x. These are the two polynomials. There exist by division algorithm, or this condition is obtained by division algorithm. So we shall write like this: by division algorithm, for polynomials we have division algorithm for polynomial ring we have proved in our earlier lecture, and we may refer that. For two polynomials where g of x is not 0, f of x is any polynomial, in f of x there exist another two polynomials. There exist q of x and r of x in f of x such that this f of x is written as q of x into g of x plus r of x. This is a theorem we have proved as a division algorithm, and this holds where what is the condition for r of x, where r of x is equal to 0 or degree rx is strictly less than degree gx. This is by division algorithm, and which is exactly the second condition of Euclidean ring. A belong to R, B not equal to 0 belong to R. There exists another pair of elements in R, Q and R in R, such that A is equal to QB plus R. Here A, B, Q, R are polynomials, and so given two polynomials fx and gx in f of x, there exist another two polynomials qx and rx in f of x, such that f of x is written as qx into gx plus rx, where the condition r of x is 0 or degree of r of x is less than degree of g of x. Hence this proves, so thus the polynomials in polynomial ring satisfies the conditions of Euclidean ring with the d function defined as degree of f of x, and this proves that f of x is a Euclidean ring. So this proves that this f of x is a Euclidean ring. Thus we have proved two results in this lecture. First is f of x is integral domain, and second as it is Euclidean ring by using the definition of Euclidean ring. I hope you will understand this. Thank you for watching the lecture.